Today we're solving problem 190, reverse bits. This problem looks simple, but it tests your understanding of bit manipulation. And bit manipulation is extremely common in technical interviews. If you can confidently manipulate bits, you unlock an entire class of problems. Let's break it down. Step by step. We are given a 32-bit integer. Our goal is simple. Reverse all 32 bits of this number and return the resulting integer. Now here's what's important. We always process exactly 32 bits. Even if the number starts with leading zeros, they still matter. We must reverse the entire binary representation. No shortcuts. All 32 bits. Let's walk through example 1. Input n equals 43,261,596. In binary, that is 000000010, 100101000, 0001110, 1001100. After reversing all 32 bits, we get 001110001, 011110000, 001000101, 0100000. That equals 964,176,192. We are literally mirroring the bits. Left becomes right. Right becomes left. Now example 2. Input n equals 2,147,483,644. Its binary representation starts with a 0, followed by 30 consecutive ones, and ends with 2 zeros. Reverse all 32 positions, and you get 0, 0, followed by 30 ones, and ending with 1 0. The result, 1,073,741,822. And remember, we are not reversing only the meaningful bits. We reverse all 32 positions. This is a bit manipulation simulation problem. We process the number from right to left using a right shift, and at the same time, we build the result from left to right using a left shift. Think of it like this. Each step, we extract the last bit, then we append that bit to a new number. Extract, shift, append. That's it. No tricks, no special cases. Just repeat this process 32 times, and you've reversed the bits. Let's start with the brute force approach. The idea is simple. First, convert the number into a binary string. Second, reverse that string. Third, convert it back into an integer. And yes, it works. The time complexity, O of 32. Space complexity, O of 32. So what's the problem? It uses extra space for the string. It does not demonstrate bit manipulation skill. And in interviews, that matters. Interviewers usually expect a solution built directly on bits. This approach works, but it's not elegant. Now, let's talk about the optimal approach. Bit-by-bit reversal. We build the reversed number, one bit at a time. Here's the algorithm. For exactly 32 iterations. First, shift the result left. Rev left shift equals 1. Second, extract the last bit of n, using n and 1. Third, add that bit into the result, using rev or equals bit. Finally, shift n to the right, and right shift equals 1. Why does this work? N and 1 isolates the last bit. Rev left shift by 1 creates space. Rev or bit inserts that bit. And we repeat this process exactly 32 times. Clean, deterministic, interview ready. Now let's walk through the actual implementation. We define a class called solution. Inside it, we implement reverse bits. First, we initialize a variable called rev and set it to 0. Then we run a loop exactly 32 times. Step 1. Shift rev left by 1. This creates space for the next incoming bit. Step 2. Extract the last bit of n, using n and 1. Step 3. Insert that bit into rev, using the OR operation. Step 4. Shift n to the right to process the next bit. And that's the entire loop. After 32 iterations, every bit has been reversed. No extra space, no string conversion, pure bit manipulation. Finally, we return rev. Let's do a small step-by-step simulation. Imagine n equals 1011. Iteration 1. Extract the last bit. That's 1. Rev becomes 1. Iteration 2. Extract 1 again. Shift rev left. Append the bit. Rev becomes 11. Iteration 3. Extract 0. Shift and append. Rev becomes 110. Iteration 4. Extract 1. Shift and append. Rev becomes 1101. Exactly reversed. Now let's analyze complexity. Time complexity, O of 32. Since 32 is constant, this simplifies to O of 1. Space complexity, O of 1. Let's cover common mistakes. Number 1. Forgetting to loop exactly 32 times. Even if n becomes 0, you must continue. Number 2. Using string conversion unnecessarily. Number 3. Confusing left shift and right shift directions. Number 4. Not understanding that leading zeros matter. Now, in advanced optimization, if this function is called repeatedly, we can optimize using memoization on bytes. Here's the idea. Precompute reversed values for all 8-bit numbers from 0 to 255. Break the 32-bit number into 4 bytes. Reverse each byte using the lookup table, then recombine them. This dramatically reduces operations, and this technique is common in systems-level optimization. Key steps to remember. Reverse all 32 bits. Extract the rightmost bit. Shift the result left. Repeat this process 32 times. Time complexity, O of 1. Space complexity, O of 1. Whenever you see bit reversal, bit counting, XOR tricks, masking, slow down and think. Ask yourself, what happens to one bit at a time? Bit manipulation problems. Reward calm, mechanical reasoning, not speed.